Nice to meet you. Thank you so much for doing this.
Oh yeah, no, thanks so
Adventure.
much inviting me, and I'm excited to be here.
Yeah, I just pinned on top your presentation if you want to click on it really quick, just so you see how the audience will interact with it. And in the
Okay,
meantime,
yeah.
I'll just share
Hmm.
really quick on Twitter that we are starting, and then we'll start in a minute if that's okay.
Yeah, yeah, sounds good.
Okay. I'm still pinging a few people in, but at least it's like when you share things, it's you don't always have access to the microphone, so it's kind of a weird
Right,
new
right.
situation.
Okay.
But yeah, thank you so much for doing this. And I know people will keep, joining. But
Right.
I think we can slowly start with introductions and
Hmm.
then go from there. And yeah, meet Frank. Frank was
Hi.
looking forward to this.
Oh, okay. Well, hi, Frank.
Hi. So the title says Dr. Alfred. So shall we call you Dr. Amroth
uh,
or
yeah, I mean,
Alfred?
whatever is easier. You can just call me Alfred, or you can call me Amrut. Amrut is my first name, but up to you.
Oh, okay. Hi.
Yeah.
Nice meeting you. Thank you as well. I mean, for coming to the club and share with us very interesting
No,
research.
no, thanks.
Very
Thanks for
frontier.
having me here. Yeah, I'm very excited. Do you guys usually have talks around this time? I'm guessing it's 9 p.m. for you, right?
Yeah, so we have different time zones depending on where the speakers come from.
Right.
Sometimes, when it's people from Europe or Middle East, then we'll have
Mhm.
like morning, like 9 a.m. or 12 p.m.
Right. Right.
sessions,
Right.
and then when it's usually West Coast or Asia, like Australia, then we switch to this time usually. So yeah,
I see.
and then also, I mean, for me, it's kind of good. Like, my kids are in bed, everyone had dinner and stuff, so it's kind of
Mm-mm-mm.
relaxing. So yeah, I think we can start. So,
Okay.
welcome everyone to Science Society, and of course, a special welcome to you, Ruth. And before we start, let me give the audience a little bit of introduction and correct me if there's anything wrong I found.
Sure.
I looked
Yeah.
up
Okay.
kind uh, um, ID link, from the paper. So um,
Right. Right.
you did your bachelor in science in physics and astronomy at the University of Hong Kong, and then also your master, and then you stayed for your PhD
Yeah.
too. Um, so, and it's really interesting that you say it must be a really great place to be as a student and to learn, because that's really a great sign. So and
Yeah.
we usually start with like a short interview. So, if
Hmm.
you could tell us a little bit about how did you discover this affinity or passion even for science and then also physics? Was it like a childhood dream, or
Um.
was it something that came later on in life?
Yeah. When I was younger, I don't know. Probably still in primary school, I'd read some. I'd come across some books that were related to space or just science in general, and I was very interested in reading a lot of science fiction by people like Carl Sagan or Arthur C. Clarke. So all of that really just made me very interested, especially in space, but also in just finding out why things work. That's pretty much physics, right? So ever since then, I've always been very, just very curious about why something happens. So I guess that just always kept pushing me to find out the reasons for how things work, I guess.
Yeah, thank you. That's really great to learn that, books are they're kind of um, forming you to have this curiosity, um, which is, it's really interesting to learn how, the different speakers that come here, how they kind of realize that they have questions about, specific topics,
Hmm.
science, and so on. Some, say when they went to a museum or when they spend time in nature or,
Hmm.
whatever it is, it's really interesting. And how did you then come to work on this project? Was it, something that kind of your supervisors guided you towards, or was it something you kind of wanted to follow? Was it easy? Was there like a lot of problems? I don't know. Was there any back peek
um,
behind the curtain story?
right. I started this research on dark matter in the, well, second or third year of my undergrad. So I joined this research group, and then they were mainly focusing on using this technique of gravitational lensing, which I'll talk about, I guess. It's a prediction by Einstein's theory, and they were using this they were using this technique to kind of figure out what dark matter is, since we don't really know yet. And well, as an undergraduate student, you don't really have much choice. You just join the research group and get some experience on what's going on. And then ever since, I continued. I built on what I was doing for my final year project, my MPhil, and then my PhD. And I guess the direction we took, which this paper is based on, it's really a mix of theory, computer simulations, and observations. So I kind of like doing a bit more theoretical stuff, but then this project ended up being, making use of all three foundations of how science is done. So in the end, it ended up being very nice, kind of a full round of the scientific method, I guess. So it was just one thing led to another, and then, well, here we are, I guess.
That's interesting, because it's. I don't think it's very common that physicists kind of mix up theoretical physics with experimental physics, or
Yeah,
traditionally maybe it wasn't.
yeah.
But um, the last speaker we had also about physics topic, one of them
Hmm.
also said, and he was also not the he was not the senior scientist of the project. He said also that he was combining these things for the project. So is it like a trend in physics now that you kind of, if you want
Mhm.
to have high impact publications like this and work on projects like this that get this high impact kind of you know
Right.
projects that you have to kind of nowadays combine this, or
Well, I wouldn't really say it's a trend, at least yet, because um, doing this kind of thing, it takes some time, because you have to, have some theoretical prediction. Then you need to, in the worst case, you need to write your code to do simulations, and then you also need to write proposals to get observations, unless you do it with existing data. And well, if you read through most papers nowadays, you wouldn't really find something like that. You might actually find something like that in the past. Like maybe in the last century, people tended to have a more global view when they were doing science. But nowadays, everything is so specific that people don't really merge all these three things together. So when you read a paper, sometimes it's really hard to. You have to read it a lot to figure out what's going on. So I think sometimes things just have to align for you to be able to do all three, like theory, simulation, and observation, in one paper. But definitely, if you can do it, then that paper is probably going to be very impactful because it's kind of like a story, right? People can read it and understand, and it's probably going to have more impact because whatever you find is probably going to be like uh, the result of some solid research, I think.
Yeah, yeah, it's interesting that you say that traditionally scientists were like more general and then became very specialized.
Yeah.
And maybe it's I asked this too, like maybe people that say yes to coming here and going through the trouble of trying out a new app and a new way of presenting, maybe it's people that are more open to like uh, gain knowledge from different things, try out
Yeah, I'd
different.
like to think so.
Maybe that's why it occurs more often. But in biology, if you want to like, or neuroscience or whatever, um, if you want to publish in Nature, you have to always, like people usually say, you have to cover three major things. Like you have to have genetics, behavior, and physiology or something, to get the Nature paper. It's really
Right.
interesting that that's not necessarily true for physics, but maybe there's a trend that just the publishers demand is now everywhere because I don't
Yeah,
know,
yeah.
but
No,
it's
for sure.
interesting.
They must have some kind of yeah, their own way to assess what probably they think would create the most impact amongst their readers. Um, then maybe they have something in their head, yeah, but we haven't been able to figure it out. But the only thing we've been able to figure it out, at least for Nature, is um, they definitely want some kind of observation. It's almost impossible to get a theory only paper published. They definitely want some observation, and then they want you to kind of link your prediction to that in a, well, I suppose, in a very kind of groundbreaking way. They don't want you to follow the what's normally done, I guess. But yeah, the editors, definitely have something in mind which helps them to weed out and pick what they think should be published.
And the funny thing is, it's more or less probably the opposite of what grant committees want.
Oh yeah, no,
Don't
that's
you think?
that's exactly right.
You get published really high if you somehow, by some miracle, got the grant approved that no grant committee usually would approve.
Yeah, yeah.
Yeah, thank you for that. And, people don't just learn about physics, they will learn about how to publish in Nature
Yeah,
too.
no, that's most of it nowadays.
Exactly. So, yeah, so as I said, everyone has access to the slides. So, if you want to go ahead and talk about your research, and then we'll follow up with questions about your research, the stage is yours. Thank you.
Okay, thanks, Katerina. I just have a couple of, I think, about you guys, if you guys can see the link, it's about, I think, 17, 16 slides. And so, I don't know how you normally do things, but feel free to stop me, or if you have questions or want to discuss something along the way. And if not, I'd like to start off with, again, thanking Katerina for inviting me to give this talk and have this discussion. It's very interesting, and I always like sharing and talking with people about our research. Um, Let me start off with why we infer the existence of dark matter, right? The main focus of our research, or my research, what we do here at Hong Kong, is we're trying to figure out what the nature of dark matter is. scientists still don't understand what it is, and we use this technique called gravitational lensing. So I'll show you what that means in a few slides. Now, if you're on slide 2, the first person to predict dark matter was this guy called Fritz Zwicky. So he's a bit of a crazy guy. He was born in Bulgaria to Swiss parents, but then lived most of his life in the US. And he predicted the existence of dark matter sometime in 1933. Now, how did he do this? Well, I'll explain that in the next slide. But Zwicky was a really eccentric guy. He was quite an odd guy, and one of the things he was famous for was for calling his colleagues spherical bastards, because no matter how you looked at them, they remained the same. Because if you look at a sphere from any angle, it remains a sphere, right? So he had really creative, really creative things like this to say. And well, for the same reason, a lot of people, a lot of colleagues or scientists that he used to work with, he worked mostly in Caltech, they weren't really fond of him. He had a lot of crazy ideas, and many of them we think now laid the foundation for modern astrophysics. But in his time, people didn't really appreciate it. It's pretty much like how Einstein never won a Nobel Prize for relativity, and now we know that he should probably have won like 5 different Nobel Prizes. He some of the other things he did apart from postulating dark matter is coining terms like supernova, which is the explosion of a star in the final stages of its life. Predicting things like neutron stars. These are very dense stars, fully made, fully composed of neutrons. If you're interested in a nice review of part of his life, I put the link on the slide. You should take a look. It's a very interesting read. Now, I'm going to slide 3 and then here I'll tell you what Zwicky actually did. So he was doing research. I think he just finished his PhD, and he was looking at images of galaxies taken through telescopes, like the one like the image you're seeing here. Now, this image is taken by the Hubble Space Telescope. It's a cluster of galaxies. We astronomers usually call it a galaxy cluster because, well, it's sort of a family of galaxies all near each other, sort of clumped up together. So all the bluish things you see on this image, they are distant galaxies in the background. So they're really, really far away, billions of light years. And each single dot you see, it's not a star, it's a galaxy. And by definition, a galaxy is at least 100 million stars, much like our sun. Now, the faint kind of yellow blobs that you're seeing, these warm orange yellow blobs, they are the galaxies that are in the galaxy cluster that Zwicky looked at. And all he did was he just measured how fast these galaxies were moving. There's a technique, and then you can actually just measure their speeds. And the speed of how fast something's moving just depends on the gravity. So, and then the gravity just depends on how much mass you have, right? So back then, the understanding was that the mass that's present, for example, in a cluster, the only contribution is from visible matter, like stars, right? Stars emit light, and they're the only things that have mass. Some of the other things that might have mass are, giant clouds of dust or hydrogen gas, basically every element we know in the periodic table. And when you sum up all the stars and their mass contributions, for example, in the galaxy cluster that Zwicky was looking at, he found that the speeds of the galaxies were way too high to be explained with only visible matter. Now, this created some problems in the field, and people had different reasons. Some people said, well, maybe the observations are wrong, but other people did the same kind of studies and found, pretty much the same results. And Zwicky was crazy enough to propose, well, a relatively simple idea. He said, what if there's extra mass in the galaxy, but it's just invisible? If you go to slide 4, I have a little video there. And he said, well, every galaxy, and probably the entire universe is filled with some invisible substance which doesn't interact with light, but it interacts with gravity. And he called it dark matter. Now, in the video, you see that there's this, kind of faint cloud, sort of like a blob of material surrounding the galaxy, the spiral galaxy, and that's how we, in modern science, that's how we think that dark matter is distributed in within galaxies. So it's, you can see it here in this video, but it's just to show you how it looks like. In reality, it wouldn't really be visible with light. But now we think that this mysterious dark matter composes about 85% of all matter in the universe. So that's a significant fraction of mass, which we don't really know what it is. It's quite crazy that we still don't know what it is. He postulated this in 1933, right? It's almost going to be 100 years. And what I mean by the remaining 15% of matter in the universe, it's pretty much everything you and I know of. It includes you, me, computers, the chair you're sitting on, our planet, even stars. They're all considered normal matter, and then dark matter is completely something different. Now, if you go to slide 5, the quest for dark matter, well, figuring out what it has been is at the forefront of modern physics, really, because it's not just important in astrophysics, it's also important in particle physics, pretty much the foundation of modern physics right now. And if you choose to accept general relativity, general relativity is humanity's current understanding of how gravity works, right? So this is what Einstein's famous for. He predicted this in 1915. And if you accept that this theory is correct, right, that's you don't have to, but if you do, then you need to invoke the presence of dark matter. And like I said, some of the first observation was how fast galaxies are moving. That's what Zwicky did. But later in the 1970s and 80s, people also looked at how fast galaxies rotate and also how light bends around galaxies. I'll talk about that a little bit later. And well, there's mounting evidence now, and that's why dark matter is considered, it's part of the current cosmological model, of how our universe works. And once people accepted this somewhere in the 1980s, so you'll notice that 1980s is when people started taking it a bit more seriously. So there was a 50-year gap, and Zwicky was dead by then. So because of his eccentric attitude and how he proposed crazy ideas, people didn't really believe or take Zwicky's ideas seriously. That's why he's not so popular to the public. If you People wouldn't really recognize his name, even in science, people wouldn't really recognize his name. And that's a pity, because his ideas were crazy and most of them ended up being right. He was just a very creative thinker. Now, once people accepted dark matter to exist, they started thinking about candidates. What kind of particle is dark matter? This is what particle physicists like to do. They like to figure out what makes up everything. And there's kind of 3 classes that you can classify the particles as, just like temperature: hot, warm, and cold. And each of these classes has different candidate particles. And nowadays we think that, based on astronomical observations of how our universe looks through telescopes, we think that dark matter is probably cold, right? And cold dark matter has a lot of candidates, even things like black holes and, again, neutron stars. But the 2 leading candidates are WIMPs, which are weakly interacting massive particles. So these are just massive particles that don't interact that easily. Or axions. Axions are a kind of new uh, particle. They were proposed after WIMPs, and then the difference is that they're very light. So WIMPs are massive, and axions are just very, very light. And in our research, we actually focus on axionic dark matter because WIMP dark matter is the current paradigm, the existing paradigm, but it has a lot of problems. What are these problems? Well, if you go to the next slide, WIMPs are a prediction of an extension of the standard model. What that means is that the standard model is our current understanding of all the particles and how they interact in the universe. This is sort of the holy grail for particle physicists and what people at CERN research on. Now, our current theories, they can't produce any particles for cold dark matter. Well, there aren't much. And WIMPs is one where you have to kind of push the boundaries and look at new physics. But WIMPs, people have been looking for them for decades now. Okay, it's been like 2 decades almost, and probably billions of dollars of funding, but scientists haven't really found these WIMPs in detection experiments like at particle colliders or other sorts of experiments. They haven't really detected these. And you wouldn't be wrong in forming the impression, if you read astronomy papers, that a lot of scientists and astronomers, they subscribe to the idea of WIMPs for no real reason at all. The axion, which is the new kind of particle, it's also a prediction where it's a prediction from string theory. So it's also a new theory that goes beyond our current understanding. But for some reason, most people really like holding on to WIMPs as their preferred particle. And what we're trying to do in our research is to say, well, let's look at how axionic dark matter performs and whether it can resolve some of the problems that WIMPs face. Because look, we've been looking for them for decades and we haven't really found them. It's better to stop hitting your head against the wall and start considering new ideas. And well, I'll be honest with you, when we sent this to Nature Astronomy, we got a lot of pushback from one of the referees, and we think this is kind of the common reaction because what we're proposing kind of goes against the existing paradigm, and people don't like that. And that's a human reaction, and you expect scientists to not really have that, but apparently they do. They still get controlled by their by their ego or whatever. It's very hard to let go of your existing worldview, and that's really not too surprising. You really have to take a step out and redefine your worldview when someone else comes and proposes a new idea. Now, if you're wondering why these particles are called axions, it isn't some nerdy reason, but the person who proposed this was Frank Wilczek. He is the Nobel laureate in 2006. And he said that, well, look, the axion, it solves a problem in physics. It didn't just solve dark matter. It wasn't just proposed for dark matter. It was proposed to solve other problems in physics. And he said, look, it solves problems in physics. It cleans up problems in physics. And he was in his kitchen and he saw this detergent lying around. I don't know if any of you have seen it, but this is a popular detergent. And he said, well, I'm just going to name it an axion. So that's really where the name comes from. Most scientists don't actually know that. Now, WIMP dark matter, it doesn't just have the problem of us not being able to detect it. It also has problems in astronomy. If you go to the next slide, you'll see one of the predictions that WIMP dark matter makes is, it says that, look, we should have a lot of neighboring galaxies around our galaxy, the Milky Way, but in observations we barely see any. Now on the left, I'm showing you an image of another galaxy, which is probably like how the Milky Way looks, and the sun would be somewhere on the outskirts of this galaxy. And then the image on the right is actually an image of our galaxy, and that's why you see kind of the disk, right? If you've gone to a very dark place, you can see the disk of the Milky Way if you look up in the sky. And all those little boxes are the neighboring galaxies. We call them satellite galaxies because they kind of orbit our galaxy like baby galaxies. And the models predict hundreds of them, but we really only see a handful, 10 or less. So WIMP dark matter has a lot of problems, not just in particle physics, but also in astronomy. So all of this is really just motivation to consider a different kind of particle for dark matter. Now, if you go to the next slide, the one of the best ways to really study dark matter is this phenomenon of gravitational lensing. So this is a prediction by Einstein, also resulting from his theory of relativity. He predicted this in somewhere like 1936. And it's pretty much just like how a magnifying glass works. He said that anything with mass, right, it bends the fabric of space-time. So the fabric of space-time, you can imagine, is sort of like a grid all around us. And anything with mass, and that includes you and me, we're all bending or warping this fabric of space-time. Now, if you look at the figure on the left, let's say there's the red background galaxy, but it could really be any light source. It could be a lamp or it can be a galaxy. And then if there was nothing between you and this galaxy, by you I mean the telescopes on the left, the light would travel in a straight line and you'd just see a red dot, right? But if there's something in between, like another galaxy, this blue blob that you see here with a lot of mass, it can actually bend the light rays from this background red galaxy. And what you'll see with your telescope is that panel, behind the red dot, where you see the blue galaxy in the center, but around it you see what we call lensed images. So, the three, I don't know if you can see, but there's three different red blobs forming a ring around this galaxy in what we see with our telescopes. And then each one of these blobs is the same image of the background galaxy. So it's kind of like you're seeing four of the same thing, or three of the same thing, really depending on the configuration. So this is really what lensing is, right? It's like a magnifying glass. It focuses the light rays, and the properties of these images, and that's really just the brightness and the position of these images from our telescopes. These properties of the images, they tell you something about what kind of mass distribution the blue galaxy has. And then the blue galaxy, we call it the lensing galaxy, typically. In the terminology is lensing galaxy because it's doing the gravitational lensing. And the background object, you call it the lensed image. Now on the right, you have this animation that kind of shows you how light from really distant galaxies travels, and then it gets bent by something in the middle. And then when it reaches you, it's all very trippy, and images start getting warped. Now, the reason, this is a very good tool to study dark matter because it just probes the mass distribution in the galaxy. It doesn't get affected by anything else. It directly tells you how much mass is in the galaxy and how it's distributed. And this is very important if you want to be able to distinguish between different models of dark matter. If you want to be able to say, whether dark matter is made of WIMPs or axions, it's very important that you're able to distinguish between what happens to these lensed images. That's what we do in our research. Now, if you go to the next slide, before I jump into what we do in our research, I'm just going to show you what typical lensed images look like. If you use the Hubble Space Telescope, it's the best telescope we have in optical. If you use it to look at very distant galaxies, you can see that they form a lot of patterns. It's really like artwork. It's not. It's just a lot of unique patterns. You see the Einstein rings, which are these blue rings around the yellow orange lensing galaxy. So the yellow orange galaxy is, it would be the blue galaxy in the previous schematic. It's much closer to us, and then the blue arcs you see around, some of them partial, some of them complete, we call them Einstein rings, and they are the lensed images of something much more distant, something much behind the yellow galaxy. And they also form things like Einstein crosses, these four lensed images. These guys are more religious. They form a very symmetric pattern. You see these four glowing points of light surrounding the lensing galaxy. But you also have other configurations, right? You have a whole host of different configurations that can really form how these lensed images can form. Now, if you go to the next slide, I guess that's slide 10. I'm sorry, some of the slides, the page number is missing, but we're on slide 10. And apart from the fact that we don't know what dark matter is, astronomy also faced this problem for over 2 decades, called lensing anomalies. And well, as the word suggests, these are just anomalies in lensing, particularly lensing of quasars. Now, if you don't know what a quasar is, it's just a distant galaxy. It's a very, very far away galaxy, and it's a very bright source. It's very, very bright. It looks like a point, and people call this a quasar because it's a quasi star. It looks like a star, right? Stars look like tiny bright points when you look through telescopes. Now, when people make what you call lens models, that's simply when people estimate the mass distribution of the lensing galaxies. Um, for example, you're seeing 4 different images of different galaxies, and at the center, that's where the lensing galaxy is. And what surrounds it is the lensed images. So you can see very beautiful, these spectacular images. It's incredible. Um, those are the lensed images. And then when people make models using WIMPs or WIMP dark matter, they find that they can't really reproduce the observed brightnesses of these images. So that's a problem, right? In science, when you have a model, your goal is to be able to predict some kind of phenomenon that's happening in nature. And when you take this to the next level, you raise the bar and go to the next slide. You use observations in the radio wavelength. So in astronomy, this means that your images are you're able to get much higher resolution images, so you see things more clearly. Scientists find that they can't reproduce the positions of these lensed images as well. So in the end, what people find is that, look, we can't reproduce anything that we see. We can't reproduce the brightnesses of the lensed images, and we can't reproduce the positions of the lensed images. And the question we ask is, this is something we do for the first time that hasn't been done before. We ask whether dark matter that's composed of axions can resolve this problem. Can we get rid of these lensing anomalies if we consider dark matter as axions instead of WIMPs? Now, if you see on the figure to the left, that's an example of how radio telescopes look like. There's, this one is called a VLA. It's in New Mexico. And I don't know how many of you've watched the movie Contact, but it's based on a book by Carl Sagan, the greatest astronomer to ever live. In the movie, they actually go to the VLA, and then you can see even on their poster, they're at the VLA. It's a very, very really nice place. And well, if you haven't watched this movie, you probably should. It's a very good movie, and won a lot of awards, I think. And really, you should just check out the books or TV show Cosmos, done by Carl Sagan. It's the book is the best selling science book ever, even now. It's called Cosmos. Um, right, and then so anyway, that was just a detour. But basically, what scientists find is that they can't reproduce observations of lensed images. Now, in our work, we consider axionic dark matter, but it's also called wave dark matter. And the reason for this is, like I said, WIMPs are very heavy and axions are very light. That's the difference. That's the main difference between them. And light particles, like axions, on very large scales, they have wave-like properties. What do I mean by that? Well, they literally behave like waves on a beach, right? If or like ripples on a pond. They undergo a lot of interference, like when you have two ripples in a pond, the waves merge together. There's constructive and destructive interference. Like you can see on the plot on the right, it's a cover photo from Nature Physics in 2014, where one of our collaborators, for the first time, did simulations of how wave dark matter should look like, and they got these very interesting patterns. You can see that the image shows two galaxies glowing in yellow, but around them you see these really artistic patterns of interference patterns between the constituent particles. Now, these patterns are something very, very unique, and it hasn't been studied before. And in our research, we ask, can these patterns correspond to changes in density, right? They're sort of like blobs of mass, kind of like granules or kind of like grains of sand. And what we ask is, can wave dark matter really reproduce uh, lensing observations? Can it account for what we see in lensing? Now, our research got published about a month ago, I guess a bit more than a month ago, and we were very happy because it got picked up by a lot of news articles. There were about 50 articles written on it, and I think on YouTube there were at least it reached about 4 or 5 million people because there were multiple science educational channels which made videos about it. So you could probably check those out, or you can ask me for the links because those people explain the stuff really well. I actually wanted to watch those videos and read these articles instead of my own paper because they wrote it so well and it was very interesting for anyone to really read. And what we find is that these fluctuations in dark matter, well, predicted by wave dark matter, it actually can reproduce lensing observations. If you go to slide 14, this is sort of a schematic that I made using a sort of like a 3D graphics software just to illustrate what happens. On the left is the prediction by WIMPs, right? WIMPs predict a very smooth mass distribution. By smooth, I mean there's no kinks or bumps in the mass distribution. It's a very smooth, it's a very big dip where most of the mass is. And then here, the object is a galaxy. And behind this, there's another galaxy, a very bright object, a quasar, if you will. And then the light rays from that, they bend around this galaxy, like what happens in lensing, and they reach us on Earth, right? And what we see with our telescopes is we have to project the images back, which is shown by these dashed lines. And what you might find is that, one of the images is smaller or less bright than the other one, right? And then you'd see different configurations like you saw in the slides before. Now, in wave dark matter, if you look at the plot on the right, the mass distribution isn't smooth, right? Like what I showed before, it predicts a lot of fluctuating, a density pattern because of the interference between waves. And then, so you can see how chaotic the mass distribution gets. There's all sorts of bumps and peaks. And then the light, so it doesn't follow a straight line. It sort of follows a very chaotic path, and it bends and wiggles. And when it finally reaches Earth, what we find is that sometimes the lensed images, they can swap in brightness. Like you might find now that the left image is brighter or bigger than the image on the right. And this is very important because this means now you can use lensing observations to kind of distinguish between different models of dark matter. And if you go to the next slide, slide 15, this is just one of the predictions we make. And the leftmost panel is how images from the WIMP dark matter model would look. And then the two panels, the central panel and the right panel, they're different versions of images that you might find if you use wave dark matter. So you can see how things are smooth and calm and nothing's happening in the WIMP dark matter model. But when you use wave dark matter, things start to get crazy and you get all sorts of these wavy patterns that you can see. And these produce very, very interesting phenomena. If you go to the next slide, slide 16, we make use of this. We first find that in our paper that the general predictions of wave dark matter are in good agreement with what lensing observations see, meaning that you can really reproduce the lensing anomalies. But we want to raise the bar, right? When you're doing science, you want to test your idea as stringently as possible so that you know that it's right. So what we do is we do a more specific test by looking at one particular object, This is a very interesting object that was seen in radio, and it showed both kinds of lensing anomalies. Basically, people couldn't predict the brightness or the position. And then the object that's being lensed, it's kind of it's a quasar as well. And if you look at the plot on the right, the center of the galaxy, what we call the optical core, is what you'd see with the Hubble Space Telescope, for example. And then the two really, spectacular jets that you see here, very, very beautiful jets, you only see them in the radio wavelength. So you need multi-wavelength observations to really get the full picture. And this kind of object, with a central core and two radio jets, was being lensed, and it was showing all these anomalies. And then what we did was we asked, hey, look, if we can use wave dark matter, can we reproduce the observations? And well, the main result in our paper is that we find out that we can. So, decades long problem in astronomy, we find that wave dark matter probably can solve this. And that's very interesting because, like I said, the WIMP paradigm, people have been holding it very close to their heart. It's very hard to get people to accept new ideas, even if they're scientists. And, they're supposed to have an open mind and look at ideas clearly, but, well, that's life, right? If you go to slide 17, and that's my last slide, the conclusion is that we find that wave dark matter can resolve these lensing anomalies. And does that really tilt the balance towards axions? Well, we need to do a lot more work to really make a claim like that. But it definitely puts axions on, the same standing, and at least when it comes to lensing, it puts axions on a higher pedestal because they can really get rid of these anomalies that have bugged physicists and astronomers for decades. We have a lot of stuff that we plan to do in the future using large scale, cosmological simulations of galaxies, and these need to be done with supercomputers. And this will hopefully give us a better idea of what's going on, and shed some light on dark matter. And that's really the end of my talk. I have more slides as backup if you guys have questions, but that's really the end of my talk. So thanks.
Oh, thank you for really this amazing talk. You explained this really so that even I could understand. At least I think I understood. Like you left me thinking, oh, cool, I know
I'm glad to
complicated
hear that.
physics now. So, yeah, thank you. No, and it was also beautiful. And yeah, so, and also Bob and other people say that, yeah, in the chat
Yeah,
you
I just
already
saw the
are.
chat. Yeah, thanks a lot. I'm hoping you guys learned something, and if you guys have any questions, yeah.
Yeah, for sure. Frank, do you want to go ahead? Abyss wants to join. We have a few people, so if you have a little bit of time left, we would for sure ask questions. Thank you.
Yeah, sure. Yes, thanks, Katerina, and thanks for Amuth for this
Yes, that's fine.
treat for the
You're too
for
kind.
all that
Thanks.
has of mind heart for science. This is amazing. Look at through the the author's eye. The I have just basic questions to understand the. There is this lensing, the Einstein ring that you briefly mentioned that there it could for various for reasons that they can project like 2, 3, and more, right? More, and
Yes. Yeah.
also with these anomalies.
Yeah.
Could
Yeah.
you go into a little bit more, to shed lights? What? So I assume that the slice number, uh, there is this drawing that you mentioned you did with the software, that the right one.
Yeah.
Is
Slide
it
14. Yeah.
14? Yeah, there's
Yeah.
no number. Okay, 14. So yeah, so there must be some connection with this, the foreground galaxy somehow. I mean,
Yeah.
warping. I mean, the model. This is why you can put a finger on, the differentiate different models, right?
Yeah.
Is it related?
Yeah. No, you're right. That's really why we can distinguish between the different dark matter models. If you're looking at slide 14, um, you can see that on the left, the prediction from the WIMP dark matter, it's very smooth. The what this grid is trying to show is the fabric of space-time, and this kind of bump that the galaxy is making, it's very smooth. It's like you put something heavy on your mattress or something like that, right? It kind of pulls it down, and that makes a set of predictions for what we see with telescopes. It tells you how bright and where the lensed images should be, and then you compare with what you see with telescopes. Now the same thing happens with the wave dark matter, but as you can see, it's the fabric becomes very messy, right? Very, there's a lot of stuff going on there because of all these density patterns predicted in wave dark matter. And then because of that, naturally, your predicted brightnesses and positions of where you expect the lensed images to be would be different. And because of this difference, and that's what makes this whole idea interesting, because if you can't test it, then it's boring, because if you can't test it, then you can't do science, right? And this is interesting because it makes these testable predictions, and then you all you need to do is look through your telescopes and see what kind of brightnesses and where you're seeing your lensed images, and then you make this kind of model for your foreground galaxy. And you need to see is, well, can I predict the brightnesses, can I predict the positions? And then that's why it's a very relatively simple test, really. um, that simple, or rather, I should use the word clean. It's a very clean test because there isn't a lot of uncertainty. There's some, but there isn't a lot of uncertainty in your models. So it really lets you rule out or guides you towards new uh, ideas for dark matter.
That's cool. So the so far the from the observation that overhead, I mean, outstanding is are those two anomalies that you mentioned, the brightness and
Yes.
positions. Are there others? So how easy these so so as you did you mention that the wave model of yours that explain it included, I mean it's a it's a larger set than the WIMPs. The explain all it can, and also explain more. Did you mention that, or can you
uh
confirm that?
yeah, you're asking really good questions. Can I know if you're like astronomer or a
No,
physicist, or
I'm also a researcher, I have to say, but yeah, I'm more on the engineering, like simple systems. I work with
ah, I see.
'cause
These are
I have
really
a
good.
deep.
Uh-huh.
Thank you. Yeah.
Well, these are really good questions. So, thanks for asking. Yeah. So the main anomalies are the brightness and position. That's what's been lying around in astronomy for about 20 years, which people have been struggling with. But it's interesting that you ask this because there's more recent observations. Well, because of advances in engineering and technology, we're able to make better observations, right? More precise observations, like the launch of the JWST, the James Webb Space Telescope. And what we're finding is that not only are the brightnesses and positions uh, anomalous, but there's also other kinds of odd behaviors that lensing systems depict. Sometimes we find that some of the images completely disappear. That so there's no model that predicts. Well, there are some models, but they don't really. You don't really expect a lensed image to completely disappear. It's as if someone kind of put some sort of shield between you and the galaxy suddenly, and that's very odd. There's been there's been some papers that suggest that maybe this is uh, related to aliens or something like that. It's very interesting. So some of the images really disappear, and we call these transient events because they're transient, they're short-lived in time, right? And then you can only see it because now we have more frequent and better observations that really lets you see this. But there's also, that their images disappear, but There's also things called time delay anomalies, where the light arriving from these lensed images, there can be a delay, between each image. Not all of the images arrive at the same time. So sometimes you might see one image, one lensed image out of four, and then you'd have to wait like 10 years to see the next one, simply because the path taken by the light rays is different. And these are called time delay anomalies, and no one's really looked at them because it's a very, very new thing. So that's also something we hope to look at, and then put wave dark matter to the test and ask, can it explain these new anomalies we're finding as well? Yeah.
Wow, that's really something that looking forward, looking forward to. Do you think this? I think this is Nobel. There's potential, a very rich virgin land, right?
Well,
For new ones.
I'm very glad you think so. It really depends on how the future goes, like what kind of work we do, following up to our nature paper, following up to our research. It's all about convincing yourself and other people, scientists and everyone else, that this is indeed a better model, or this wave dark matter is a correct description of dark matter. So, and to do that, we need to do more tests, look at more observations, different lens systems, and every single time we need to ask, can wave dark matter explain these? And in the coming year, we're planning to do this kinds of tests on more systems, and we've already done a test on another system. It's a supernova that's being gravitationally lensed, and we found that in that system as well, wave dark matter can explain the data. So there's no a priori reason for it to explain the data in that different system, because they're completely independent systems. The fact that the predictions kind of match is very, very interesting, and that makes us even want to try it on more systems to really see what's going on. So definitely, understanding the nature of dark matter is at the forefront of physics. If you can actually do it, the person who does it is gonna, not win one Nobel. You might end up winning like five Nobels. Who knows?
That's so cool. I'll yield my mic. I have more questions if there's more time. Yeah, and so I'll come back. Yeah, Katerina.
Yeah.
Yeah,
Thanks so much for the nice questions, Frank.
yeah. Thanks, so I'll follow you. Yeah, hope we can see each other offline.
Yeah.
Yeah, thank you so much for the questions. It was really interesting to listen to. And Kirko, do you want to go next? Yeah, please
Yeah,
go.
I do. And this is crazy how the conversation just went between you and Frank, because it goes like right into my question. I know nothing about any of this, right? But
Yeah.
well, at least from what I was like understanding, like, and this is, I guess, let me just get the question. So, if let's posit that dark matter is kind of does have like a wave type of property. And I was
Hmm.
just thinking, like, like how light moves differently through like a medium like water than it does
Yeah.
like through normal space. Um, so I was just wondering,
Yeah.
like, 'cause if, let's say if you were to vibrate the container with the water, um, like the image kind of like looks a little weird too.
Hmm.
So is it possible? Because you also just mentioned like how there's kind of like a period sometimes in which you can see the effect of the lensing. So I was kind of wondering, could that possibly be contributed to like large scale movements of dark matter? Because like
Hmm.
you show some like a variety of images, right? Where like the one
Yeah.
in the first slide of your presentation, and then I think it's like slide 14, where it's got like
Mm. Yeah.
the smooth version versus like kind of the more fluid version.
Right.
So like my brain, how it kind of thinks about it is like if there's like a gravitational point, and like let's say dark matter is like affected by gravity equally as like normal
Yeah.
matter,
Yeah.
then it may have like the some word for it, a higher likelihood of like forming circular structures if the um, the force is acting in like one direction from like from itself towards all directions. Uh,
Yeah.
but then like it would also make sense that if there's different amounts of it
Hmm.
of like dark matter in different places, that like there could be like a higher concentration or more coming from certain directions. But you would
Mm-hmm.
think over time that would like smoothen out, like just through
Mm-hmm.
like the nature of like gravity and like particles moving and
Yeah.
whatnot. But like if it's a wave, then the image would like kind of not always be the same, or it may not look at all like what it looked like before. So when you were saying like, I guess my question is this: it has there been situations where you look at an image, and the next time you look at it, you know it's the same spot, but the image itself is different from the actual lensing, if that makes sense.
Yeah, no. What an incredible question. Yeah. That was a you have a really that was a really nice way of putting it. Uh and how, how lensing happens. It's exactly like what you have said. I mean, that analogy you used of kind of water and then the refraction and then different distributions of dark matter affecting the images. That's exactly what happens. That's one way to model it, and that's really what happens. And yeah, when we look at more recent observations, part of some of the projects that I'm on, some collaborations that make observations with the Hubble Space Telescope, we find that, yeah, you look at the same spot, you're looking at a lensed image, and uh, one year it's something, and then the next year it's something else, right? So it's changed, and this is something we don't really see before because we just didn't have frequent observations of the same thing. To see this, you kind of need to look at the same thing. And now the understanding is, probably if we made more observations, we'd find out that, these lensed regions, regions where lensing happens, kind of lights up like a Christmas tree. There's things blinking in and out of existence, and there's a lot of hypotheses that have been proposed by people to explain this kind of thing. Some of which say that, yeah, it depends on the nature of dark matter, how it's distributed, like different amounts of dark matter through the galaxy, that can cause these variations. But these are very new things. It hasn't been, there's no satisfactory explanation yet, really. And we mostly see this in galaxy clusters. So galaxy clusters is massive, massive lenses. They're the most massive structures we know in the universe, and we're only starting to appreciate this better with observations from new telescopes like the James Webb Space Telescope. Uh, and people are only starting to realize the really odd things happening. It's actually incredible. Um, I hope that answers your question.
And this is amazing. I'm so glad I saw this along the day.
Well, thank you so much. That makes my day to hear that. That's the kind of reaction I want from my audience, right? You should uh, join in on our research. I really like how you how you phrased your question, and I could almost see how you were visualizing how the whole dark matter and lensing process is happening. It's very nice to hear it uh, from someone. And I think you said you don't work in lensing or astronomy, right? So
Yeah, I
that was
mean, I've
very
never
nice to
taken a
hear.
physics course before, so like I just watch a lot of YouTube.
Well, yeah, I do the same. Teaching is really the quality of teaching's dropped a lot. But anyway, thanks so much for that question. It was very nice to hear.
Yeah, thank you. Mr. Ali, did you want to ask a question?
Yes, thanks, Katrina, and also thanks, Ambrose, for very
Yeah,
interesting talk and
thank you, thank you.
outstanding achievements. I have three quick questions, and I was wondering if you could address them. The first is about uncertainty in your models. So I would like to know what are the sources of those uncertainties, and how you manage that, if you considered.
But so by uncertainties, you mean kind of uncertainties in the model?
Yes.
Yeah. Okay. That you're that's a good question. So what we did was, in lensing, for your lens model, right? Your model for the mass distribution of the galaxy. The uncertainties arise from what we call a degeneracy. So, the parameters that you use to describe the mass in a galaxy. It's always a model, right? We don't actually know the real distribution of a galaxy. We always Humans always have to use some kind of analytical estimate. um, these parameters, things like ellipticity, or the amount of mass you have, or even the position of your mass model, these can all vary, and you can actually have multiple models that produce the same results. So because of that, you can imagine there will be a lot of uncertainty, because like 10 different models give you the same results, then you don't know which one to pick. There's no reason to pick one over the other. So to explore this level, of how many models you have that can produce the same data, or the tolerance or the error in your lens model, we use something called a MCMC sampling. So it's a statistical technique. It's called a Monte Carlo Markov chain method, where you kind of do like a random distribution of your model parameters, and then you see, what kind of tolerances you have in your model.
Yeah, honestly, I was thinking of doing high throughput Monte Carlo with machine learning to
Mm,
find the optimum case for that tolerance. Do you agree with
right.
me on that?
Yeah, no. So, Monte Carlo is the way to explore this. And then so we do the MCMC for the smooth model. And for the wave dark matter, the way we actually make the models is using random fluctuations. It's like a Gaussian random field. That's what we call it. So we haven't been able to use MCMC for wave dark matter because we don't really know how to do it, because the fluctuations are random, and we're not really sure yet what the framework would be if you wanted to approach it with MCMC. And then, of course, we haven't done any work with AI or machine learning with this aspect, but it's definitely becoming more popular, because we're having more and more telescopes, and the amounts of data we have is in the terabytes. So people can't do it anymore. Individual people can't do it anymore. You can't use undergraduate students anymore to go through the data. So I think it's definitely the future, to use machine learning as well as these kinds of statistical methods like MCMC.
Okay, great, thanks. And my second question is about the magnetic anomalies. Analysis. So, we have you also thought about the considering this magnetic effects in the model?
Um, so we don't typically, when people do lensing or make lens models, they don't consider any electromagnetic effects. And then the reason is because that's why I was saying lensing is a very nice probe of dark matter, because it just traces the path of gravity. It doesn't actually care about any of these electromagnetic interactions. And so the main influence is from gravity. But yeah, I actually went to a conference in Spain last week, and there was this guy there where they were exploring uh, some aspect of how light behaves, like the polarization of light. And they were trying to say that depending on the polarized depending on how polarized your light is, you might be able to distinguish between different models of dark matter. And so this is related to the polarization is related to the magnetic field. So there might be something there, but I just don't know, because it hasn't really been considered before.
Yeah, because of the wavy corona you have there. I thought if we have magnetic field in the galaxy, so they may be able to bend the light, and we get different patterns for those waves. That's the reason I thought it may affect the final pattern you get in your simulations.
Right. Yeah. So we in our simulations, we think that the gravity is what would trace the path of the lensed images, because we aren't looking at the polarization. So the electromagnetic effects wouldn't really have a role, we think. But maybe that's something to consider. Maybe that's something to think about. We haven't really thought about it yet.
Thanks a lot. And my last question is about the pattern. Have you thought also about the finding specific patterns for those waves and see what type of patterns they follow. And by changing, for example, going from one galaxy to the other, or by changing the characteristics of the lens, galaxies, how these patterns can change.
Yeah,
Um,
no, right. No, that's another incredible question. It's a very good scientific question, and yeah, we're looking at what kind of patterns these galaxies make, um, and what kind of density patterns these galaxies make. Like one of the examples in slide 14. That's just one example, and in this paper, we've only done one test of a specific galaxy. We looked at the general, sets of patterns that are made, but we also look at only one specific galaxy. And then we're working on another paper now where we look at another specific galaxy. So there'd be that one would have a different pattern. But that's really how you need to do it to figure out whether wave dark matter is the better model. So definitely, looking for these patterns and understanding how they change is future work. That's what needs to be done. Yeah.
yeah, thanks a lot. I think if we have, yeah, definitely in the future we may be able to develop some mathematical equation taking into account all these, features
Hmm.
as input parameters that can give us some predictions without doing a lot of, expensive models.
Yeah, no,
Thanks a lot.
I'd be happy to talk to you about that later. You can always reach out to me through email or something like that.
Sure, I will follow
Yeah.
you and then we'll be in touch with you. Thanks a lot
Great.
for your
Yeah,
interest.
thanks.
I
Yeah, no
appreciate it.
worries. Thank you. Thank you.
Thanks, Katrina.
Yeah, thanks for your questions. Abyss, do you want to go ahead?
Thanks, Kat. Thanks, Armut. This is actually really groundbreaking and sort of exciting to see that axions are starting to take more prestige compared to WIMPs. I think
Can you guys
especially
see
those.
them?
It's very faint. I can hear a little bit.
Can you hear me now?
Yeah, it's slightly better.
Oh, okay.
Yeah.
Um, so what I was saying was that it's good to see that axions are taking precedence compared to WIMPs, which is sort of like I think at least like as far as I know, the experimental settings to detect WIMPs is kind of repurposing neutrino detectors. So it's really nice and exciting to see that your work and essentially where you're gonna go with this. Um, so I do have a lot of questions, but I'm just gonna ask two for
Yeah.
starters, and then if time permits, I'll ask more. So the first one is that I guess Kirko actually asked this question. Mine is sort of related to the dark matter halo. So do you see some kind of asymmetric gravitation due to this wave nature that you kind of simulated, or do you even expect to have asymmetric gravitation because of the wave nature of axions?
Yeah. Thanks for the question. And well, that's what we see when we make these wave dark matter models, because of all these density patterns. From the interference um, of the ultralight particles, they get all these patterns, and those patterns are really just asymmetries in gravitation. They're not a smooth gravitational pull, but you know all sorts of gravitational pulls from different directions, and then that's really why we see these variations to the lensed images and all these patterns. So it is all sorts. It's a very asymmetrical thing that's going on.
I see. And also, I think in the slide that you have not discussed, sort of like I think the appendix slide
Right.
22, if I'm not mistaken,
Hmm.
your model is actually sensitive to stellar concentration. So I'm just wondering, does it depend on the type of star, if it's like main sequence, or if you have a heavier star-like formations, sort of remnant stars like neutron stars, white dwarfs, or even sort of rogue black holes for that matter?
Well, you guys are amazing with all these crazy good questions. um, yes, so it is sensitive to the amount of stars in your lensing galaxy, but what it's sensitive to is not the type of star. It's sensitive to the total mass of stars, or rather the distribution of the stars, like how they're placed in the galaxy, and that determines some of the properties of these lensed images. But I think it's interesting that you bring up neutron stars and black holes, because I haven't talked about that, but that's a different phenomenon called micro lensing, where they create, they're not able to make changes to the positions of images, but they're able to make changes to the brightnesses. And depending on the mass of the object, and then, neutron stars, black holes, or normal stars, they have different masses. Depending on the mass, the amount of amplification in the brightness you'd see is different. And that's what these micro lensing astronomers do. They look at these micro lensing observations, they're just light curves, and they say that, look, if it's a neutron star, can we explain it? If it's a black hole, can we explain it? And then they rule out the potential objects of microlensing. People even consider wormholes. Wormholes are also a prediction of general relativity. Also, although we see that in sci-fi all the time, it's a real prediction as well. So you can definitely constrain the type of object, but with a specific kind of lensing observation, these are micro lensing observations.
I see. That actually does make sense. And yeah, the last one is just not sort of a comment, not question, but I'm really glad that MCMCs are also used in your work. I've used it
Hmm.
before, but more like in biomedical imaging. But
Hmm.
it's kind of fascinating. But yeah, I'll pass the mic to the next person so we
Thank you,
have
thank
more
you,
people
thanks so
on
much.
stage, and I'll
Yeah,
ask more questions later. Thanks. Kat,
thanks.
back to you.
Yeah, I wanted to also check in with you, Amruth, how much time you still have.
Oh no, I'm happy to take questions all day long.
Oh, really? Okay, you're
Oh yeah,
perfect.
yeah.
Okay,
I mean, that's the fun in doing science, right?
yeah, that's true. Dr. Brown, did you have a question? Please go ahead.
Yes, I did. But first of all, Amrit, that was a really great, I guess, talk. I'm surprised that I was able to follow it as closely as I was, but I learned a lot, and I think it was really great work.
Thank you, thank you. I'm really glad to hear that.
I do have two questions. The first one I had already asked in the chat, but I wanted to see if you could add any bit more. I'm kind of just curious as to generally just the peer review process,
Yeah,
specifically when it comes to like really complex crazy physics like this. Like,
yeah.
I know in the slides you have shown, you had like some models that you had done where you're just comparing the simulated work to like actuals, and like obviously because they align, then you're kind of suggesting you're in the right direction. So with the
Yes.
peer review process, is it just a matter of someone just reviewing your code, or actually just running it and trying to like replicate it, or just like what would that actually look like?
Yeah. So what actually happens in the peer review process, they don't actually tell us, because all we get is the comments from the referees. So we have to make the code available, right? So that people can replicate what we do, and including the referees. And then so Nature especially, they pick 3 referees. So that's a lot more than the typical journals, where sometimes it can just be one referee. And then I from what I know, I don't think that referees ever do a full replication of your results. More so now than before, simply because it takes too much time, and then referees don't actually get paid. So it's sort of like community service, really. You can just reject any referee request because you don't get anything out of it except helping the community, right? So they usually, referees are also people doing research, and they really don't have the time to fully replicate someone else's study. And also, if it's a simulation, they might not have the funding, or sometimes the equipment. So what they usually do is, and then that's why it's important to get senior expert referees in the field, because all they look at is, they look at it, and then based on their understanding, they look if it makes sense. They look at the other literatures we cite, and then they try to form a coherent picture, and then assess how reasonable it is. Some of them might use the code to do some basic tests, but I doubt anyone ever does a full replication. So that's why, because our work is the first of its kind, now we need to wait to see what other people do, and we also need to do follow-up work from our end as well.
Awesome. Thank you. That made sense. And then the second and last question that I have, while not very specific to what you had just shared, kind of just something I wanted to ask, just because you're someone who works on like the field of gravity and specifically dark matter. I'm not a astrophysicist, by the way. I'm an engineer, but I'm very interested in all this stuff.
Cool.
One thought that I had when I was kind of just looking into the conception of dark matter, what observations it was that kind of informed it being thought of in like the subsequent work. Um, in kind of the field of engineering that I do, fluid mechanics, when we're kind of looking at, say, flow through a pipeline, we have like a set of equations to calculate like pressure drop for specific velocities if it's like laminar flow, and then if it's turbulent flow, you use like a second set of equations for that. And I was kind of trying to analogize that with gravity as a whole, where obviously we have like Newton's conceptualization of gravity that kind of works for everyday life when we're here on Earth. It works for like solar system scale, it works for a certain scale, but when it gets to higher scales, like of course in this case of like galaxy clusters, we find that things don't necessarily hold true then, and that's kind of why we have to start invoking dark matter. And then also in like the quantum scale, we also see that like our current model of gravity also doesn't work on those scales. So I kind of had this thought just based on my own experiences. Is it an outlandish thought, or maybe a thought that has been looked into and has been like scientifically disproven, of gravity kind of behaving where it has this phase transition where on one scale you have a certain set of equations that govern gravity, and then at a separate scale you have a phase transition where you have to use a different set of like models or equations for gravity, as opposed to invoking dark matter, if that question makes sense.
Oh, so basically saying whether there's some sort of formalism where you could explain away these observations without invoking the presence of dark matter. Is
Yes.
that what you mean? Yeah. So yeah, like I was saying, if you want to invoke the presence of dark matter, you need to use general relativity, which is Einstein's equations, right? The Einstein field equations, which tell you how mass bends space-time and how space-time tells mass to move, and everything kind of trickles down from the Einstein equations. But there's people working on alternative hypotheses. Uh, oh, I don't have that slide. I think I have that slide somewhere else. There's people working on an alternate hypothesis which say that we don't need dark matter. One of this is called modified Newtonian dynamics. It's called MOND, and there's people working on these alternative theories where they try to say that, look, we can explain these observations without dark matter. But up to date, all these alternative ideas have struggled to explain all the crucial astronomical observations that need to be explained. For example, some of these MOND models, they can explain how fast galaxies move or how fast galaxies rotate without using dark matter. But most of these, they really struggle to reproduce gravitational lensing. They really struggle to produce the effects that we see in lensing without adding in extra mass. So, I'd like to think that it's good that people are exploring these ideas, but up to date in the field, all these ideas, they struggle to reproduce one or more of these astronomical observations, which we think has to be satisfied by any model that you want to take seriously. For example, another one of these observations would be the cosmic microwave background, right? The static you see on your TV. Um, it's sort of what it's one of the primary evidences for the Big Bang. And one of the co-authors in our paper, he actually, George Smoot, so he actually is from the US, and so he was the Nobel Prize winner for working on the cosmic microwave background in 2004. And any model, any cosmological model needs to be able to explain observations like this. So it's some of these alternative ideas without dark matter, they really struggle to do so. But people are still working on it.
Interesting. Awesome. Thank you so much for the answers, and I look forward to hopefully hearing more from you in these rooms.
Right. Yeah. Thanks a lot.
Yeah, thank you. Rolf, I know you've been waiting for a long time actually. I'm sorry, my PTR I think got messed up in between Rolf and then John. Do you
No,
still have a
no
question?
problem. Yeah, no problem. I'm patient. I've got time. Great talk. Thank you, Amuth.
Yeah, thanks a lot.
Amruth, am I saying it right?
Yes, yes.
First, real quick about Mond. I've listened to these different theories. I think to defend the alternative theories, I think you would agree that dark matter also still has gaps and is not a complete explanation for all the different observations, right? So each of the different theories has problems. There is no one, perfect solution as far as I understand it. Is that correct?
Yeah, yeah, that's right. That's right. It has problems as well,
Mm.
and
Yeah.
like this lensing thing. So which we just resolved. So it's just the problems it
Right. Right.
has that people think that the severity of these problems aren't as severe as the other models. So that's why most scientists
Yeah.
subscribe to dark matter. But definitely, all these models have problems. Yeah.
One of the things I don't like about Mond is because even though some of the predictions appear to correctly match observation, in some cases better than dark matter theories, the problem they have is they don't have an actual explanation for what's the causality of it. They just say it just does. The equations
Mm.
fit. So as you get further out in the galaxy, the dynamics change, but there is no physical explanation. It's only a
Mm.
mathematical equation. And I hate things that don't have an underlying physical
Yeah.
reason,
Yeah. Yeah. You
So
you
what I
and all
like about dark
scientists.
matter is it makes sense. Yeah,
Right.
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 So
Um,
I have a couple of questions. The first would be axions versus WIMPs. I might have missed if you'd explained it, but what is the basic difference, and why do people? Are you running into resistance because people don't like the axion theory, and what would be their resistance to it?
Yeah, yeah, it's that's a nice question because that's kind of more important for science than the result itself, how the rest of the society perceives it, right? And we're getting a lot of pushback, and it's not just us. So axions have gotten a lot of pushback in the field for quite some time now, and this is really the case for almost any new idea that kind of tries to overthrow the existing paradigm. And like how Einstein tried to overthrow Newton's laws. And this is really yeah, it's really common. And he even got this resistance from one of the referees for Nature Astronomy. And the referee, all his referee comments were on the introduction of the paper, so it wasn't on the science or the research. It was on the introduction where we said that, look, the WIMP dark matter model, the WIMP paradigm has faced a lot of issues and they have yet to be detected. And then the referee insisted that they don't have any of these problems and they can be you can solve all these issues. So he claimed that WIMP dark matter doesn't have any problems. And that's just ridiculous, because in the introduction you just do a literature review, right? You don't There's no
Right.
science there. So,
And
and
what?
then
But
even the
sorry,
editor and
what
the
is
other
the
two referees, they
difference?
yeah no they I mean, I was just
Could you
saying that
tell us really quickly? Yeah, sorry,
yeah,
I
no,
shouldn't interrupt.
even the editors and referees, they thought it was ridiculous that this referee is acting like this, but that is really the common reaction than the rarity.
So, for the sake of laymen here, including myself, is there any way you could really quickly just explain the basic difference between axions and WIMPs?
Yeah,
Unless
well,
you already
WIMPs are.
covered that, I might have missed it.
Oh, sorry. Yeah, I mean, if you missed the first few, like the WIMPs are just massive, right? They're weakly interacting massive particles. So the mass of the particles is much larger. It's predicted to be much larger, much heavier. For example, than a proton, like 10 or 100 times heavier than a proton. While axions, they're thought to be very, very, very light. So they're called ultra light particles. So their masses are tiny, incredibly tiny, way tinier than an
I see.
electron.
I see.
Yeah. Yeah.
Okay, interesting. Well, that does kind of lead to my final question, and you don't have to spend long on this, but this is more of a bigger question. And you briefly touched on people basing everything on relativity. We know that the relativity equations work, but the underlying going back to explanations again is this concept of space-time. And I
Mm.
personally have always found that as a dubious basis, which and in a way, to me, the presence of dark matter might ultimately explain what we used to call space time. What if dark matter is the real fabric of space, almost like a medium in which all these events occur? And the very reason that things attract and bend is due to space time. It is the fundamental fabric of space, or close enough for our purposes to be fundamental. And then maybe that becomes the explanation, and we can kind of rethink our terminology of space time and maybe ultimately dispense with it. Do you have any thoughts on that?
Yeah, no, I mean that's an interesting way to look at it for sure. And really, the big breakthroughs in understanding for humanity as a whole, right? Humanity's understanding of the universe. These big breakthroughs come when you do away with assumptions that you make, and things that you think are true, but then they actually aren't. And then this might be one of those cases, yeah, where we don't really know what space time is, right? It's a mathematical construct that we use to explain what we
Yeah,
see.
definitely.
We
Yeah.
don't actually measure something, or we never there's no evidence for the existence of space time. So it's very interesting, yeah. Maybe there's some hypothesis or theory that comes out where people try to explain observations, making this assumption that space-time is dark matter. um, but I think what you're saying is how science should proceed. Asking questions like that instead of trying to dig a deeper hole down down something very specific, because that isn't
Yeah.
going to give you the global understanding that you need to really understand how the universe works, and which I think is the pitfall in modern science nowadays. Everyone's digging a very deep hole and into something very, very specific, but we need to have a breadth of knowledge instead of depth of knowledge. I think. But yeah,
Yeah, I
it's
like that.
interesting, and I think
Definitely.
people should definitely look
Awesome.
at it like
Yeah.
that. Yeah.
Thank you.
Yeah. Thanks for the interesting question.
Okay, thank you so much. John, you have the last question, if that's okay. Thank you.
Yeah, that's my honor. Yeah, thank you so much. Actually, I have a couple questions regarding dark matter. See, when we talk about dark matter, yeah, dark matter. So, if dark matter, see, the follows the rules of gravity,
Mm.
are we supposed to think of dark matter itself, although we cannot see them? Can we imagine them as a interglacial, see, cloud, or as a dark matter stars, or they
Hmm.
form galaxies, dark matter galaxies, or do
Hmm.
they see like a form, see like a just see basically diffuse, see like just hydrogen molecules
Hmm.
inside the universe?
Hmm.
So how do we
Yeah.
see? How do we feel? See like see for example, in our galaxy, or see visible galaxy, do we
Hmm.
have a parallel, see like a dark matter galaxy, see within us, or it just for me
Mm.
it's difficult to
Yeah.
imagine, because see, when we talk about that dark matter,
Mm.
what dark matter means
Mm.
light can penetrate through it,
Hmm.
so that means it's dark matter. But right now you tell me that dark matter actually can form, see, those kind of huge mass and then have gravitational
Mm.
lens effect.
Lensing.
That
Yeah.
means it must be a, see, like a huge mass, right?
Mm.
In order to have this, see, like a see
Yes. Yes.
huge concentrated mass,
Yes. Yes.
in order to have this lens effect.
Mm. Yeah. No, that's the this is just a stream of brilliant questions and comments. Um, it's everything you said. Uh, there's dark stars. The entire galaxy is made of dark matter galaxies. There's clouds of dark matter, and then there's dark matter going through you and me right now. Particles of dark matter whizzing about in your room. And you're right to sufficiently bend light, like what we see when these galaxies bend light. You need a lot of dark matter, and that's why we think the universe is 85% of dark matter. And the current understanding of dark matter and how it's distributed is that it is concentrated at the center of galaxies. There's a lot more dark matter at the center of galaxies, and then it smoothly falls off as you go outwards. It reduces in density as you go outwards. So it's pretty much everything you said exactly. It's just this dark matter everywhere, and we think it's concentrated at the centers of galaxies. And then that's why when you look at galaxies or galaxy clusters, you see this effect. And if you look kind of like an empty patch of sky, you wouldn't really see much. But yeah.
So okay, so if within our solar system, we have
Yeah.
lots of dark matters, then but the problems when we calculate our solar system, the Mars movement, Mars mass, sun's
Mm-hmm.
movement, sun's mass, we don't consider those dark matters effect,
Mm-hmm.
right?
Mm-hmm. Yeah. We don't, because the density of the dark matter is still so low that the effect that the distribution of dark matter would have on these orbits, for example, in our solar system, is very, very small compared to the effect from other objects nearby, like other planets or other moons. So, if you wanted to be able to see this, if you wanted to be able to measure this effect, you'd need very good equipment, which none of our technology has the precision to distinguish. So that's why people don't do it, because you just can't see the effects.
Because
Yeah.
in my understanding is the dark matter, the concept that come out is because when people measure the movement of those stars at the edge of the galaxy, and at the center of the
Mhm.
galaxy, find the stars movements. Actually, they surround the or orbiting surround the center of the galaxy. It's
Yeah.
pretty much the same. So that's why they see, okay, there must be some kind of dark matter
Mm.
is at the edge of this galaxy, our
Mhm.
galaxy, and so
Mhm.
that makes them move faster. Or
Mhm.
so, but as you see, if you see, but most of the dark matters, if most of the dark matters actually is concentrated in the center of the galaxy, our
Mm.
galaxy, so would that contradict to those original thinking that there are more dark matters outside at the edge of the galaxy?
So, with respect to the observations of these stars orbiting the galaxies, and then rotating around even at the edges of the galaxies, their speeds of their orbital speeds, how fast they rotate the galaxy, it only depends on how much mass, how much total mass the galaxy has inside. So there doesn't actually need to be dark matter, or there doesn't need to be a lot of dark matter at the edge of galaxies to make the stars go that fast. It's kind of like centrifugal force, right, where the mass at the center is what determines how fast these stars are orbiting. Um, so there's no real way for us to tell whether there's more mass at the edge than at the center. And then all the observations right now, they suggest that there's most mass at the center, and then less and less as you go out. But all these observations, like the rotation speeds of stars and galaxies, um, they're determined by the total mass of the galaxy and not the distribution itself. The only thing that probes the distribution is lensing. So that's why gravitational lensing is a very nice tool, because that one really depends on how much mass you have exactly at all places, at all positions.
Hmm. So another I read it somewhere they talk about fourth dimension. So if we have a fourth dimension, would that be a dark matter is within the fourth dimension, so we cannot see them, but they are there?
Mm-hmm. Yeah,
Is that
there's a
possible?
lot of Yeah, well, no, there's a lot of hypothetical hypotheses that have been put out there, and axions are a prediction of string theory, right? So string theory has like 26 dimensions or something like that. And then we don't even know what goes on in these dimensions. Everything is a mathematical construct. The only thing we know is that our current universe is four-dimensional after Einstein's theories. So that's why it's called space-time. So the three dimensions of space in the x, y, z directions, and then the one dimension of time, the arrow of time, which goes from past to future, which we also don't understand why, really. But so that's 4D, right? That's already space-time. But there's theories that say that dark matter could be some kind of unknown force in in the fifth dimension, or the sixth dimension, and then there's a lot of ideas out there. The real trick is to be able to come up with an observation or experiment which lets you test this idea. Um, that's the hard part, and people haven't come up with how to do that yet. So all of these ideas are just they remain hypotheses until a good test can be people can come up with.
Yeah, thank you. That's actually
Thank
an
you.
interesting point. Yeah, thank you, John. That I wanted to ask, like in the end, but so what technological invention do you wish for, basically, in order to, to continue with the work and have like hard evidence? Is there something, you could wish for, but it's like still unrealistic? Thank you.
Um, well, yeah, that's there's a lot of things I want with technological advances. I'm sure we all do. But one of the things would be just better telescopes, and you stare at a part of a sky for a long time, so you have like an entire video, rather than just images from telescopes. You have like a whole video of what's happening. Well, let's say, if you look at a galaxy or galaxy cluster, that would be incredible, because that, we don't have videos of the these kinds of lensing events, because these observations are so costly, so expensive, equipment wise to make. But who knows, maybe sometime in the future, technology would be so good that you'd be able to really see the sky at every point in time, and then see what's happening uh, at each point in time. That would be incredible to see. I suppose that's one of the things that would be nice.
Yeah, well, yeah, that would be amazing. I can imagine that it would be amazing to look at, and yeah, hopefully we'll get there. Do you think like quantum computing or something like that would help, or make it like, wouldn't that make any sense? Or neuromorphic computing to basically increase capabilities of computing power and make it cheaper, and you know.
Yeah, yeah, sure. That would help a lot in doing simulations. But right now, at least, we're less bound by computational capacity than observations. Um, we just don't have enough observations, or maybe we do, but we just don't see it. Like how the answer stares you in the face, but you don't see it. Maybe you need something like AI or machine learning, or some kind of artificial intelligence to put together all these wide range of observations and come up with some coherent idea. Right, our human brains can only process so much, so maybe we're just limited by how big our brain is, or by our imagination, and maybe it needs, with these things like quantum computing, stuff like that, e- these things would definitely have a breakthrough. But probably the bigger breakthrough would come from having better observations. Something to add is, instead of all these things, if we just spent our money to look for aliens or something like that, you can just ask the aliens what dark matter is. You don't have to find out for yourself. You can just learn from them.
Okay, so cheating. No, I'm
That's not
kidding.
cheating if you get help from the smarter
I
kid
know.
down your neighborhood. It's
I'm
sharing.
joking. Yeah, I'm joking. Yeah, that that would be amazing. And Yeah, it's interesting what computing power and AI did in the biological field or protein research, and coming up with new protein foldings and new ways of looking at these problems and inventions, and it's accelerating pretty fast. So yeah, would be really interesting to see if
So
they can
so
come up
you
with actually something new.
right, right. So is your you're working in neuroscience, right? Do you have some perspective on,
Um,
how research in your field, whether it would have ties to any of these computing
well, yeah, I used a
that
lot for like mental health type of
hmm
research, mental state research,
right.
especially language and so on. So yeah, I used machine learning a lot. Um, but I always think we have so much data, like probably in neuroscience is a little bit the opposite, or in biology right now. We have a lot of labs producing a lot of data. Of course, we could have always more, but I think what we lack is something stitching it all together to make sense out of it, and then actually developing new therapies and so on that actually work for people, and that would be more personalized. We can get where we would need more data is like an N of one data. Like that's a new thing. It's like, to have from that person throughout their life more data so we can have more personalized treatments in the future and preventions. I think that type of data in the future will help a lot of people as long as we put it in the right context. And the thing is, AIs, but it has to be combined with humans because AIs can also make really dumb assumptions. So can
Right,
we. So we
right.
kind of have to
Mm,
still help each other, I think.
mm,
Um, yeah, but in that field, I think it will do a lot. But it's probably a little bit different because, in your field, we
mm,
see kind of behavior. I mean, that's kind of what you see with the galaxies. We see behavior, outcome, and then differences.
mm.
I don't know if you can really compare that and protein folding. There's only so many ways, I guess, you can
Mm-hmm.
fold those things. So I don't know if you can really compare it one to one.
Right, right, right. Well, that's really interesting, though. Um,
Yeah, we had a speaker that was really interesting. She was working on a type of machine learning computing for chemistry and so on, that you could basically ask why, and she published that. It was a preprint on the stage when she presented. It was really interesting and a really interesting talk, and they made a company out of it because I think that's what we
mm,
need to really make sense out of how sometimes these machine learning models come up with a result and causality.
right, right, right. Yeah,
So once that works, then we're gonna be good, I think.
yeah. I know that's for sure.
Hey, I got one more quick question, if I could, Katharina
Yeah, it's Amru's call for me for sure.
or Emruth, if you want. All
Yeah,
right, sweet.
yeah, yeah.
So this
Of
is
course.
this may be like a little bit off like topic, but it still has to do with kind of like the wave, potential wave nature of dark matter. So
Yeah.
uh, positing that it is moving in a like a in some type of wave type of nature. Um, its movement is affected by gravity. So, itself has its own like gravitational
Mm-hmm.
pull.
Mm-hmm.
So we know that gravity can also move as waves.
Mm-hmm.
So knowing that, is it possible that like colliding, like large colliding masses of like, or I guess maybe potential gravitational waves be affected or created by colliding masses of dark matter versus the normal way. I guess that's part one. Then part two, knowing that gravitational waves can affect matter, is that a potential way to detect dark matter by using the gravitational? Like, if we can localize spots where we know there's not like a black hole or
Mm.
neutron stars or any massive thing colliding to create gravitational waves, if that's like a potential way to
Yeah. Yeah.
measure it, you know what I'm saying?
Yeah, no. I can't believe, the questions you guys are asking again, because these are very, you guys are like all astronomers or something. I've got to be getting punked here. No one here is a is a general audience, but everyone here is like a specialist astronomer. Um, yeah, gravitational waves get affected by dark matter. That's one thing, and if they're produced by whatever source, like the collision of black holes or neutron stars. Um, and then they get affected in the same way that these light gets affected for lensed images. But the collision of two dark matter, I don't know, balls, um, that hasn't been studied. I think I've never come across that. And definitely, when people work on gravitational waves, what they can do is they try to constrain what kind of objects collided, or they try to infer, and then they say, look, it's a neutron star and a black hole with this mass, and this far away, and that's what they do. But I've never seen any work for saying that it's a collision between dark matter. That would be interesting to be studied, I suppose. I've never seen that, but and probably it would have different signatures, and I have a feeling that with the current observations of gravitational waves we have, it's probably a bit difficult to constrain. But I've never seen any work on that, so that's uncharted territory. But it definitely sounds like a brilliant idea to explore.
Yeah, the only thing I remember, we had the speaker here that talked about peaks in dark matter. Like, his hypothesis was that around a black hole, if there is a star and a dragging star, basically,
Mm-hmm.
there's a difference. One gets sucked up and the other one doesn't, but there's a difference in the drag. And
Mm-hmm.
that is because he hypothesized that there's a peak of dark matter around these black holes, and
Mm-hmm.
that reflects like the drag of the second star. I have to look it up because I'm not expressing it correctly. I don't know if you read that paper.
Um, it sounds familiar, but I don't think I read anything like that recently. Um, but I could imagine, just based on it's
Mm.
probably an idea simply based on how much energy is being released, because there are some ideas that dark matter particles can sort of annihilate, like how matter and antimatter annihilate. But that's the only way I can think of how they would be able to say something about the dark matter there, I guess. But I haven't read this paper, so I'm not too sure.
So, yeah.
Yeah.
Okay, yeah, I have to look it up better. Um, we
Right. Right.
Yeah, but I have to look it up better. But I can share then the paper with you
Yes, please.
once
Yeah,
I
no, I'd
find
be
it.
interested to take a look.
Yeah. Um,
Makes me think of something else, or we're running out of time.
what are you thinking of? I was also thinking about the previous talk with that we had with where they did the double slit experiment with photons, but not like they did the double slit in time basically, and kind of showed that light is more a wave, and then they also showed how it was kind of interesting, very interesting material science, also
Mm.
reflecting like how fast the materials they use could detect these interferences and so on. But that was also really interesting because you talk a lot that the representation in waves basically So I thought there was an interesting relation there, but maybe it's just me because I don't know enough.
No,
I
I
think
mean,
it's all
you know,
related.
this,
I agree.
yeah, yeah. No, yeah,
Sorry.
this whole you know, particle wave-like thing, um, we're seeing it in all sorts of objects, and that's what happens with wave dark matter as well, right? Because it's particles, but because they're so light, they show this wave-like behavior, this, what we call the wave particle duality. And yeah, you know, we've always seen it in laboratory experiments on Earth, but we've never really seen it in astronomical scales. And this is one of the few cases where you can see the these effects on, you know, large scales, like spanning millions of light years, billions of light years. So it's very interesting to see that, you know, at these scales, as well as, you know, inside a room on Earth in a lab.
Katerina,
I
what you
found the
made me think
paper.
of.
Oh,
Can
Oh,
you
nice.
good.
read?
Cool.
I'm sharing it in the
Oh,
chat.
thank you. Yeah, yeah.
It's indirect evidence for dark matter density spikes around stellar mass black holes. So yeah, it has been suggested for a long time that there would form a density spike around a black hole, but there was never really promising evidence. And he did, you know, a mathematical basically model that fits really well the data they collected with the between dark matter and the companion stars can satisfactorily explain the abnormally fast orbital decays in two
Right.
binaries.
Right, right. So this
Anyway.
is just probably from the gravitational effect of the
Yeah,
orbiting.
exactly. So you have like two
Yeah, yeah.
orbiting stars and one gets dragged,
Mm,
and that the data, this dragging data basically reflects
right.
really
This is
well.
haven't really seen this paper before, and you know, the authors are also from Hong Kong. It looks like,
Yes,
so
yeah,
that's
yeah,
pretty.
he presented Man Who
Oh, they
Tan, he
presented it
presented here.
in here.
Yes,
Oh, wow, that's
yeah.
really cool.
I have the
Um,
PowerPoint and everything. I
oh,
can share.
then can you share them to me? Because I'd be
Yeah, yeah,
interested
I
to, you
can
know, take
share.
a look at
I'll
that.
send an email.
Thanks. Yeah.
Okay, sure. Sorry, Rolf. Please go ahead, and then I'll think we let Amos go.
Okay, yeah, just quick thing that it made me think of was frame dragging, because you were saying the stars get dragged. And I keep occasionally coming back to what is the cause of frame dragging right around the Earth, if you're familiar with that. And the question would be, could that be another thing that could be explained by dark matter? The same way we have a dark matter halo around a galaxy, could there be small scale dark matter differences in density and so on? And could there be a bit of a, what do you call it, a differential rotation that is actually a lag effect, like the entrainment is the word I'm looking for. This goes back
Mm,
to even the 19th century. They had theories
mm,
about could the local environment around the Earth be somewhat entrained and dragged, and
mm,
they described it in different terms. But now, since relativity, we call that frame dragging. Well, what if
mm.
it is the quote unquote medium of the dark matter that is partially entrained by the rotating Earth, for example, that causes frame
Yeah.
dragging?
Right. Right. No, that
Yeah.
that. Yeah. Yeah. I've come across some of these ideas proposed by people, and I've never come across this one where they try to, you know, consider the frame dragging due to being, you know, from dark matter. Um, you know, I don't see why not, but I also haven't seen work which quantifies the level of the effect you'd see. So that would be very interesting to
Yeah, it
see if
might be
someone
really
made a
hard.
prediction. Yeah, to
Yeah, I
see, you
wonder if
know.
it makes it
Yeah.
hard when it's on a smaller scale, right?
It definitely does. It
Um,
definitely does. Yeah,
mm,
it is very difficult. That's one of the problems, because the density of the dark matter is still so low that um, you need like really really precise instrumentation, and you know, human technology just isn't there. So that's really one of the reasons I
right.
think it's very it's very difficult, and that's why, you know, we need to look at these massive objects far out in space, like, you know, entire galaxies or entire galaxy clusters. Yeah, definitely. That's I'd say that's, you know, the primary reason why we haven't, you know, people haven't looked into this.
It reminds me of there's a guy called Edward Dowdy who questioned the results of light bending around the sun. He was doing these experiments with microwave radiation passing by the sun, and his tests showed that the curves of bending do not match conventional relativity. In other words, it's not entirely by gravitational, that he believed it was partial bending caused by the plasma limb around the sun. And I always thought, well, that's an interesting idea. Could we test a comparison between a star that has a large plasma corona versus a planet, a large body that does not have a large atmosphere like that, and do a comparison? So if you could do it, shine light past Jupiter and see if it follows the correct Einsteinian bending versus, say, the sun, and could you then conclude something from that? But again, I got a feeling that smaller bodies like Jupiter, you can't easily do those measurements, is my guess, but I don't know.
Yeah, no, you're right. I think the effect would just be so minute that it would be hard to do. But I can see how the plasma would also kind of refract the light, causing additional bending or taking
Yeah.
some of the bending away. Um, but yeah, a lot of really interesting things that we could test. But yeah, we're limited by the technology, and again, this one, I suppose, is one of the cases where we just can't easily distinguish. Yeah.
Well, thank you so much, and thanks for answering Abyss' question in the chat. Sorry that we kind of missed that before.
No worries.
And
Yeah.
well, thank you so much for this wonderful presentation and for answering so patiently all of our questions. Really appreciate it. And yeah, I hope you enjoyed it. And we for sure did. This was an amazing
No,
discussion.
yeah, thank you so much. I mean, it was incredible to have these discussions. It was very nice, and the questions were really. Uh, I mean, I was very surprised by how good these questions were, because usually I don't usually get that many imaginative, penetrating questions from the audience like this. So it was very, very nice for me, and I'm very happy and thankful that you invited me, and for everyone attending as well. Yeah, yeah.
Yeah, no, for sure. We are very thankful for you going with it with our questions from, this very different ways of thinking, backgrounds, knowledge levels. Yeah,
Yeah.
it requires also some sort of availability to do that, to go with it. So yeah, thank you. That's
Yeah,
why it
for
was so
sure.
much fun and so interesting. And yeah, maybe you come back one day with updates, and somehow a lot of more devices are being feeding you a lot of more data and
Yeah,
movies.
yeah, with
And
with
then
another Nature paper in 10 years, right? Yeah, no, I'd love to come back someday if we have something interesting we find, and I'm actually interested to attend like some of these talks that you have planned. That I was just going through the list of previous talks, and then one scheduled for the future. Everything sounds interesting, really. Um, I can't believe that this is done so frequently. How do you manage to find speakers?
yeah.
It must be so
uh,
hard. Like it's so hard getting people to agree to talk about something because everyone likes to say no.
I don't know why. It's really funny. I expect always people to not respond, and a lot of people don't. Like I just read broadly articles about science in general, and then if it's in my field, of course, I read the papers right away. But then if I think it's really interesting, I go and check the paper, and then I check. Then I just write the authors, and then we also have on Wednesdays the science news where we kind of discuss these articles. So it makes me also like I never learned so much since we started this. Like this was kind of during COVID times a little bit unorganized, and then we started our own real club for this and stuff like that. So yeah, since I started this, I never learned so much in my life about all kinds of different um, science fields, and it's not like, you know, I explain it well, but in my brain it makes sense, and then I fail when, like before, I tried to explain what the talk was about, and but yeah, we just learn a lot, I think, and it keeps us interested, and yeah, and people, nice people like you answer yes, and people are mostly very nervous about it because to present this way, but then it usually works out, and people seem to enjoy it on both sides. So that's the ideal situation, at least.
Yeah, no, thanks so much for hosting this thing and for people coming, and um, it was very, very nice.
Yeah, and good,
Very happy that
and
I did it.
enjoy your next interview that you're having. So
Yeah, yeah, it's on that YouTube channel, and they run this page called Universe Today. I don't know if you've seen that, but um, so it's really looking forward to that as well. But yeah, yeah.
that's so exciting, you know, and not just 3 people around the world are interested in your work, but a lot of people. I
Yeah,
feel
no, I
like.
mean, we think all most of the science actually comes down to the communication, right? And the presentation. If you don't communicate your science, then it's just you haven't really had an impact. And so, we at our group and myself, we're I'm a big fan of Carl Sagan. And he was the best popularizer of science in general. Again, you should watch or read Cosmos if you guys haven't. And you know that really inspires. After you watch Carl Sagan or even Richard Feynman, when you watch them give talks, and then they can really captivate the entire room, and then everyone in the room understands. You just know it. You just know that they do. When you watch stuff like that, you're like, damn, I want to be like that guy. So I value communication a lot, and it's always very nice to have fresh ideas from people outside the field. So it's always very nice.
Well, you definitely are following his footsteps because, you know, as I said, I felt like it was really good to understand the concepts and so on. So you're really doing an amazing job. And yeah, we are very curious to hear more from you. And yeah, it will be fun if you would come back one day. And I will for sure listen to that interview too. It will be for sure wonderful. And good luck for everything. I hope you get a lot of fun toys that you talked about that you want to have in the future and a lot of funding. And yeah, we'll just expand our knowledge truly about the universe. So that's really exciting. So thank you.
Yeah, yeah. No, thanks a lot, Kat.
Okay, and thanks everyone for coming, asking questions. It makes the discussion so much more interesting. And yeah, I hope to hear you all again soon. We'll have a science newsroom tomorrow. So yeah, come for that if you would like. Thank you.
Hey, real quick, Universe Today, is that Fraser Kane?
Yeah, it is. It
Man, I
is.
love that channel. That's so cool.
Yeah, no, me too. I was really excited when he reached out and said, "Look, do you want to do an interview?" I was like, "Hell yeah!"
Nice.
Thanks. Yeah, and if you guys are interested, it's I think it's on Friday, Friday morning, I think. Um, yeah, yeah.
Perfect. We don't have anything planned on Friday, so let's all go and listen to that. Wonderful.
Sounds good.
Yeah, I can send out just if you tweet about it, I'll retweet it, and then people will see it.
Yeah, yeah. No, I'll get the exact time and maybe a link from Fraser, and then uh, and then get back to you.
Wonderful. Okay, that's a wonderful ending. So I'll close the room in 3, 2, 1. Bye, everyone. Thank you.
Thanks.